Hi there. As we start chapter 3, we're going to look at 3 different types of functions in this chapter. One of them is going to be exponential, and that's what we're going to focus on today, looking at exponential growth and decay. And I have some examples here where we're going to see that. One of the nice things about this chapter is it's very applicable. There's so many things that we can look at formulas and real life examples of where these types of functions occur. We'll also look at logistic functions. That'll be tomorrow. And then we'll look at logarithmic after that. Let's start off with what we kind of already know about exponential functions. This is kind of our standard form of an exponential function. On our toolkit, on day 1, we graphed exponential functions. If you look down here, this was one of the parent graphs that we had, y equals 2 to the x power. Had a horizontal asymptote at the axis and increased exponentially. We also had an exponential decay example where you're drifting off very rapidly. The big difference between these two is this base of the exponential. If you look back at the standard form of an exponential, that base value is your b. It's what you're taking to a power. The a value is always going to be your initial value. The initial value occurs when x is 0. If you look at these graphs right here, x is 0. If you were to put 0 in for your exponent, for your x, well, anything to the 0 power would be a 1. That's why your x or your y-intercept or your initial value when x is 0 is 1. Happens over here also. If you take 1/2 to the 0 power, you're still going to get 1. Now that's going to change up when you stick a coefficient on that. Right here, if I put in a 0, b to the 0 is 1, but then I end up multiplying it by a, and then that becomes, well, it's just going to equal a, so that will be your initial value where it crosses the y-intercept. This is going to be important that you remember that part of it. A is going to be your initial value. B is what we call the growth factor. If b is less than 1, then it's going to be exponential decay. If b is greater than 1, then it's going to be exponential growth. There is one other way to show decay. In the example down here, I have it as a fraction, a 1/2, so that's less than 1. That's what makes this be exponential decay. But there is another way to show that and not use a fraction here. If you think about what would bump that 2 to the denominator, well, your exponent could be negative. If you had a negative exponent, it would shift it to the denominator. It's just a different way to show the same thing. So let's jot that in our notes because that will happen, that the b value might be bigger than 1, but it has a negative exponent. So 2 ways to show decay. We're going to focus on this function today and being able to write equations using that formula. On this one, I was just going to have you watch and do this. You don't have to do this one in your notes. You can if you want to, but I've got another one just like it that I'm going to have you practice on. Here's what we've got. I've got a table of values here. I know that it's going to be exponential just because they told me it was going to be exponential, and I'm going to come up with an equation that would work for these data points. The very first thing, now I have a whole bunch of data points I could use. I'm going to hand pick the ones that are going to make my life easy. And to begin with, I'm going to start with the 0, 4. This one right here. That's going to be a nice ordered pair. If I plug 0 in for x and 4 in for my y, let's look at what happens. Now, it starts off and it's just a g of x equals a b to the x. I'm trying to figure out what a and b equal. Plug 4 in for the y. Plug 0 in for the x. Well, b to the 0 is just a 1, and 1 times a is a. A must equal 4. Now, here's the deal. That's the last time I'm going to do that. And I would just as soon you not go through that process. Look at your table. We already talked about it. I spent quite a bit of time talking about it. When your x is 0, that's where your initial value falls. Your initial value is 4. Your initial value in the formula is a. I really could have just put a 4 in for the a and called it good right off the bat. I would encourage you to do that. I'm not going to do this anymore. All right, the next thing though, I don't know what b is. I'm going to start over here, back to my g of x equals, but this time, since I know what a equals, I'll plug it in. And then I'm going to use a different ordered pair. This time I'm going to use, and I can use any of them, but I'm trying to keep my life simple, so I'm going to put in a 1 for the x and a 12 for the y and see what happens. B to the first power, that works out nice. I'm just going to divide both sides by 4, and I have my b. Now, if I had used a different point from the table, for instance, if I had used this one, I would have plugged a 2 in for the x, which would have gotten me a b squared, and somewhere along the line I would have had a square root both sides. By choosing the 1, I don't have to mess with it. At this point, I know what a equals, and I know what b equals. Let's write the function. G of x is equal to 4 times 3 to the x. That's the function that represents our exponential table there. Now, I have another one of these that I want you to do all by yourself. So take a second to pause the video and try to work through it on your own, and then you can start the video up again. All right, I'm going to assume you went through that one, and I'm going to go ahead. We're going to do a lot of examples, so I'm just going to move ahead. Here's another way to do that same type of thing, only instead of me giving you this big table that you really only used 2 points from, I could give you a graph, and notice I only give you 2 points from this graph. Start off and you write your standard equation here. And let's fill in as much as we can. Well, right here, I gave you the initial value. When x is 0, y is 4. Let's plug that in for our initial value. I'm not going to do all the algebra for it. I just know a is going to be 4. Then I'm going to use the other ordered pair to find out the b value. I'm going to plug 3 in for x, and I'm going to plug the 1.185 in. Oops, let me erase that. I'm going to put in the 3 there for the x value and go solve. Let's divide both sides by 4. Got my calculator ready to go. Sort of. Here we go. 1.185, and I'm going to divide that by 4, and I get a 0.29625. That is plenty long. Here's the deal, and this is going to be the case for this entire chapter. I'm not going to write all the decimal places. I'm going to maybe only write 2 decimal places, maybe 3. I'll go 3 this time. But you will have to keep track of all the decimal places. With exponentials, those decimal places 4 digits down really make quite a difference after a while. It will be important that we have the entire value. There's a couple things we're going to do to keep track of that. One of them is to use that second answer button on your calculator, which is second negative key. Anytime you want to reuse a number from the previous step, you just do second answer. Instead of typing in 0.296, I'm going to use second answer. Right now, I need to cube root both sides. I find the cube root button in my math menu, so I go math. Number 4 is the cube root, and instead of typing 0.296, I'm going to type second answer. That'll leave all the digits there. Looks like b is equal to point. I almost thought it was going to be 0.6 repeating, but it's not. It stops repeating. Now here's the deal. I'm going to write 0.67, but I'm always going to remember that that full value is very important. For what I'm doing, I'm not going to use this equation to do anything further in this particular example. I'm happy with my 2 decimal places. I'm just going to write y equals My A value was 4. My B value is 0.67 to the x. And this problem, actually, I think I created this, and I had intended for that to be a 0.6 repeating, or a 2/3. But since this got rounded off by me doing that, it got rounded off. So then when I did my computation here, everything was off just a little bit. No worries, just use your 2 decimal places and move on. Okay, and before I do that, let me talk about one other thing. So we used second answer here. The other thing that we will be doing is storing that value so that we can use it later. We'll do an example that has that store button. Here we have an example of some populations of a couple different cities. This particular example, we are only looking at Columbus, but you have some sort of a problem on your homework that deals with the El Paso data. So we're going to ignore that. Let's look at Columbus. All right, it says assume the growth is exponential. When will the population of Columbus surpass 700,000 people? I have the population of Columbus from 1990, and I have it from 1996. They're telling me it has exponential growth. I'm looking at when will it actually get to the 700,000. What I really have here are 2 ordered pairs. Just like the previous problem where I gave you a table, what I actually have on this, that first one is 1990. I'm going to make that be time 0. And the population 632,945. There's one ordered pair. The other ordered pair, since it's 1996, would be 6 years later, so I'll use a 6 for my x value and its population. I have 2 points. They want me to, well, they don't say this, but what I'm going to need is that equation that shows the exponential growth. I have 2 points. I've done it about 3 times now. Let's fly. I know the initial value. This is really more like what we're going to be doing, things that don't have beautiful, perfect numbers that you can just look at and tell. I'm going to use the second ordered pair. To find the B value for this problem. I know that the population is growing, so it'll be a B value that should be bigger than 1. I'm going to divide both sides here. I have 1 point, and again, I'm going to round off. I'm going to just write 1.04 is what that is, but I'm going to keep the entire value in my calculator. Okay, I goofed up earlier there. Did you catch that I put an X up here? I don't know if it's going to let me erase it. Oh, yep. That really should have been a 6 because I know the X value for that Y value. Sorry. B to the 6th power. And this is kind of weird. I have to 6th root that. In your calculator, you find that in the math menu. You have to type 6 because you're going to 6th root. Then go to math, and it's number 5. And then type second answer. I have a B value equal to 1.006. That's all I'm going to write, but I'm going to need more of that because I really haven't answered the question here. All I'm doing is writing the equation. And I'm going to write it as this. But I'm going to need more than these decimal places. So that's the starting point, and I'm going to store that 1.006 number. It's what I'm looking at on my calculator right now. It was the last computation I did. So I hit store, S-T-O. It's over there by the 1 and the 4 button on the left. Store, and then I'm going to store it as an alpha character. So I press the alpha button, and I'm going to store it as B since it's my B value. Store alpha B, enter. And now it has taken that entire value, put it in my calculator as a b value. Now, the next part of this is really answering the question is, when will this population surpass 700,000 people? That's a population. That really needs to go in for y. But I would have to solve this equation, and the x that I'm solving for is up here. And I can't really x root both sides. If you'll recall from college algebra, I'll end up needing to do a logarithm. Now, today I'm not teaching logarithms, so I'm going to show you another way, kind of an initial way how we would solve this, which is just graphically. Because this is greater than 1, I know it's an exponential growth function. And I want to know when that exponential growth hits 700,000. I'm going to graph it. I'm going to look at it as an exponential. And then I'm going to graph a horizontal line at 700,000 and see where it hits. Let's type this into our calculator. You kind of need to be doing this with me or pausing the video and doing it, because it's a lot harder to do it on your own after if you haven't practiced. I'm going to type in y equals that 632,000, and then instead of the 1.006, I'm going to do alpha b to the x power. And then let's fix our window on this. And your x is your time or your years. I'm going to go 0, 2. And then you have to think about, how many years do you think you need to open this up to before Columbus is going to hit 700,000? It's not like 4,000 years. It's not going to be that. So don't get crazy. Don't do a zoom fit, because it gets crazy with zoom fit. Use your brain. I'm going to say in 30 years, let's say. That should be plenty. For my y's, that's my population. I'm going to go anywhere from 0 to, well, I know I'm shooting for 700,000. I'm going to put in a max of 800,000 and scale it by 100,000. Now, if you hit graph, you should be able to see that equation. And I know it's exponential growth, but you hardly see it as exponential growth. Recall that anytime you use your graphing calculator to solve a problem, you need to be sketching me a graph. And what I'm looking at really looks like this. You can hardly tell that it's exponential growth, but there it is. And then I'm going to go to y equals, and I'm going to put in a horizontal line at 700,000 and graph that. And it should cross nicely. I'm looking for this spot right here where that exponential hits 700,000. To find that, I do the intersect. So you're going to hit second calc, which is your trace button. Number 5 is intersect, and it's asking me the intersection of what? So it says the first curve, and up at the very top you can see it's using y1, yep, that curve, and the second curve, it automatically went to y2, yep, that one, and then it wants you to make a guess, because sometimes equations cross more than once, so you have to scoot your cursor over close to the spot you're looking for. And that's what the guess is. Press enter, and it'll shoot back that intersection point. This intersection point is at 16 point, I'll go 16, and then 700,000. All right, let's look at what that means. The question is, when will it surpass? I got the spot right here. Your x, remember, is your time. It's your 0 or your 6, or in this case, it's 16.16. It looks like we were talking 16 years later. If I started at 1990, 16 years later would be in 2006, or maybe 2007 if it happened, depending on what month we're talking here. I'm going to go ahead and write 2016. I always like to see your exact answer, your mathematical answer here, and then you can adjust your answer, your official answer here, as long as you have that supporting mathematical answer to justify it. That way I might accept 2016. I could probably also accept 2017, and I'd be content. All right, that takes a little bit longer when you're looking for that y value. You have a few of those on your homework. Let's keep going. I have one more formula that you're going to need to know. and it's a population growth formula. It's actually the same thing as the other one. Let's look at it. This is your ending population. That's like your Y value, your ending amount. It equals P sub O, which is your initial population. That's kind of like your A. This right here is your growth factor. If this ends up being bigger than 1, this is like your B value. If it's bigger than 1, then it'll be growth. If it's less than 1, it'll be decay. The growth factor, R, is the growth rate as a decimal, but they usually give it to you as a percent. You can see up here I'm giving it to you as a percent, written as a decimal. And then T is your time. It's like your X value there. It's really the same formula, only this you have to remember how to calculate. In this example, it tells me that I have an initial population of 1,000. I'll put that in. It's increasing by 5% each year. I'll put that in. And then I'll use the function to decide what the population will be in 10 years. Let's write it. Ending population is actually what I'm looking for. The initial population was 1,000 times 1 plus 0.05. You can probably just do that in your head and call it 1.05. To the T, time, they told me 10 years. Notice this is an easier problem because I'm looking for the Y here instead of looking for the X. I can just type this in my calculator. I don't have to graph it or anything. Let's just type it in. Just on your home screen. 1,000 times 1.05 to the 10th. You should have a population, and this is the population after 10 years, would be 1628.89, and I know you can't have 0.89 of a person. That's just my mathematical answer that I want to see, and if you want to come over here and say that's really only 1,628 people, you can do that. All right, another weird type of problem, it's a doubling problem. Suppose you have a culture of 10 bacteria put into a petri dish. The culture doubles every hour. Predict when the number of bacteria will reach 1,000. Answer in hours and minutes. All right, got it. I'm going back and thinking of my population. This is going to be my ending population equals my initial population was 10 times, now here's where it gets weird. It'd be a 1 plus R, but it doesn't give me the percent. But if you think about it, if something's going to double, it increases 100%, which would be a 1. I have a 1 plus a 1. This is going to end up a 2. And in fact, I'm not really going to overthink that in the future. If it's doing a doubling type of problem, my B will always be a 2. If it's a tripling problem, my B is going to 3. If it's a half-life problem, then my B will be a 1/2. And it's to the X. There's your function, and then you fill in your information, predict when, so I'm looking for X, the time. I put an X, I could have put a T. We'll reach 1,000. So I put in 1,000 for the population, 10. Well, tell you what, I'm really not going to do this algebraically, so let me erase this, and probably I'm going to go back and I'm going to do this like we did the Columbus, Ohio one. I'm going to type this into my function, into my Y equals. I'm going to clear out my old stuff. I'm going to type in a 10 times 2 to the X. And I'm going to type in an equation. I want that population to be 1,000, so I'm going to type in a horizontal line at 1,000. I'm going to have to adjust my window. I'll leave it 0 to 30 for right now, but I sure don't need my Y's to get to 800,000. I know that I'm looking for when it reaches 1,000. I'm going to put in 1,200 for a max. Change up my scale, graph it. Since I'm using my graph, then let's look at it. I have this beautiful exponential with a horizontal line. I'm looking for this spot. Where do you find that? Do you know on your calculator? Should be doing second trace. Number 5 is intersection. immediately asks you for the first curve, press enter, second curve, press enter, make a guess, scoot your cursor over if you want, and it tells me the intersection. 6.64 is when it will be 1,000. I need this 6.64 number. I'm going to grab that. Now, they want it answered though in hours and minutes. Since it was doubling every hour, my units currently are in hours. I've got to take this 0.64 and turn it into minutes. It's going to be 6 hours, and then in your calculator take that 0.64 number. And this is not going to be that big of a deal as far as rounding. If you're just going to take 0.64 and multiply it by 60. And I have a 38.4. If you want to get crazy, you can go into seconds if you want. I'm just going to be happy with my 6 hours and 30. I'm going to go to 38 minutes. And there's your answer. One last thing. As you do these exponentials, you're going to find that we come across something we call the natural base. It's a base e. We've been working these problems that look like a y equals 2 to the x, or something you have a base of 2, or a base of 1/2, or something like that. The natural base e occurs in nature a lot, and it's like a number, like pi, that goes on forever, doesn't end, and it approximates to 2.718. Instead of seeing y equals 2 to the x, you'll see something like y equals e to the x. And there's a button on your calculator for that. It's second ln. It's right above your store button. If you ever want to take e to a power, which we typically do, it's exponentials, we're typically taking that e to a power, you just hit second ln, and it'll pop up E2, and you get to type in what power you want to take it to. Be looking for that E to pop up in different formulas that we'll use. All right, that's all we've got for exponentials. Good luck.